In this next example, we're looking at the function f of x equal to x divided by the quantity x squared plus 1. And our goal is to get an idea of what this graph looks like. First, we're going to find the first and second derivative so that we can use those to find our relative extrema and also determine whether our function is concave up and concave down by using the second derivative. So first, finding the first derivative, f prime of x here, we're going to have to use the quotient rule because notice here we have a numerator and a denominator. So recall that the quotient rule looks like denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and that's all divided by the denominator squared. So starting out with the denominator, which is an x squared plus 1, and then times the derivative of the numerator, which is just 1. Derivative of x is 1. Minus, and then we take the numerator, which is x, times the derivative of the denominator, which in this case the derivative of the denominator is 2x. And then that's all divided by the denominator squared. So we have an x squared plus 1 quantity squared. Okay, now when we simplify this, we can combine the positive x squared with the negative 2x squared to give us a negative x squared, and then we still have a plus 1. And then that's all divided by x squared plus 1 quantity squared. And there's our first derivative. Alright, now to get our second derivative, we're going to take the derivative of the first here. So again, we have to use the quotient rule. So we take the denominator first, which is an x squared plus 1 squared. So there's the denominator, times the derivative of the numerator. So taking the derivative of the numerator, we have a negative 2x. And then now next we subtract from that the numerator, which is a negative x squared plus 1, times the derivative of the denominator. And we're going to have to use the chain rule here on the denominator. So we have times a 2x squared plus 1, subtract 1 from the exponent, which gives us 1. Now the derivative of the inside, which is 2x. And then this is all being divided by the denominator squared. So we have an x squared plus 1 squared squared, which is going to make it to the fourth power. Okay, so now let's work on simplifying the second derivative. We have an x squared plus 1 in the first term and an x squared plus 1 in the second term. We also have a 2x and a 2x in both terms. So we can factor those out. So we're going to factor out an x squared plus 1 and also a 2x. So then we are left with, in the first term, we still have an x squared plus 1. So we factored one of those out. And then we have a negative 1. And then minus, in the second term, we still have the negative x squared plus 1. We also still have a 2. But we factored out the x squared plus 1 and the 2x. And then we still have in the denominator the x squared plus 1 to the fourth power. Now notice we can simplify the x squared plus 1 in the numerator with one of them in the denominator. They will cancel, and we're left with an exponent of 3. So here we are still left with a 2x, and then simplifying what's in the brackets, we have a negative x squared minus 1, then we have a plus 2x squared and a minus 2, all divided by the x squared plus 1 cubed. Alright, so we are left with then a 2x, and then combining the negative x squared and the 2x, we have an x squared, and then a minus 3. And then that's all divided by the x squared plus 1 cubed. And there is our second derivative. Now if we look at f of x, f prime, and f double prime, what is the domain of each of those? Well, we do have a denominator, but our denominator in each of those functions is always going to be positive. So the denominator, we never have to worry about the denominator being 0. So the domain of each of those functions is all real numbers. So negative infinity to infinity is the domain of each of those. Now let's find the critical values of our function. So to find critical values, we want to look at the first derivative, and we want to determine where the first derivative is equal to 0 or where the first derivative is not defined. Since the first derivative is defined for all real numbers, we don't have any critical values created by the derivative being not defined. So we're going to set the derivative equal to 0. So setting f prime of x equal to 0. Well, setting this function equal to 0, we're interested in when the numerator is 0. When the numerator is 0, it is equal to 0. So subtracting 1 from both sides, dividing by a -1, we have x squared equal to 1. Now taking the square root of both sides, we get that x is equal to a positive or -1. Let's go ahead and plug our critical values, -1 and 1. Let's go ahead and plug those back into our original function f of x to get the corresponding outputs for the critical values. So if we plug a -1 into our original function, we have a -1 divided by a -1 squared plus 1. So we end up with a -1/2. And then if we plug a +1 into our original function, we have a 1 over 1 squared plus 1. So we end up with a +1/2. So our critical points then are a -1, comma -1/2, and then +1, +1/2.